The leptogenesis is the one well-known example of the baryogenesis model to explain the baryon asymmetry of the universe. Already we discussed it in the videos about electroweak baryogenesis. And today I want to talk about several bugs and other bounced ones in the leptogenesis. So the leptogenesis, and I will explain the several things today, but through the washout for the weak washout and the strong washout regime. And the second one, I will turn to the CP asymmetry epsilon. And the third, I will discuss the Flyby effect. And next, I will discuss the low energy scale leptogenesis, like as a resonant leptogenesis or the ARS leptogenesis. And finally, I will talk about this resonant leptogenesis model and the new frontiers. And all the tasks and the formulas is based on the GPT, and some plus it comes from some academic paper. So first of all, I will discuss washout. The washout means that the generate asymmetry is erased by the inverse process of the decay or scattering. So the leptogenesis occurs by the decay of the heavy neutrino. The typical decay channel is the heavy neutrino N to the lepton double L and the Higgs double H. And there are two different channels. The one channel is the decay to the particle, but the other channel is the decay to the antiparticle. And there are also the inverse process which erases the generated asymmetry, and this is called the washout. And we can divide the two wisdom of the washout. The first one is a strong washout, and the next one is a weak washout. We can define the decay parameter K, which is the latest between the decay light of the heavy neutrino, gamma D, and the Hubble expansion light at the temperatures is a scale of the heavy neutrino's mass. And when the decay parameter K is larger than the 1, this is called a strong washout. So in this case, the decay light, the interactions one is stronger than the expansion light. So the decay and the inverse decay is comparable each other. But in the K is smaller than the 1, such a regime, the decay, inverse decay is much slower than the expansion light, is called the weak washout regime. And we can reparameterize the decay parameter K. The decay waste of the gamma D is given by the such a form with a dimensional analysis, where the Y is the Yukawa matrix and the Mn is the heavy neutrino mass. And also in the denominator, Hubble term is given by the T square through the M Planck, and we will insert the T to the heavy mass scale. And by considering this, we can define the effective neutrino mass from the seesaw mechanism relation. Then the decay parameter K is reduced to the M tilde over the M star, whereas M star is related with such a reduced Planck mass and some factors of the effective number of the relativistic degree of freedom. So the K is given by the M tilde over the M star, and such M star is given by the 10 to the minus 3 electron volt, which gives the boundary between the weak and the strong washout for the active neutrino mass. So what happens for each regime of the washout? The first one, in the strong washouts, the asymmetry is erased by the fast inverse decay. So the initial asymmetry is the erased. So the binary asymmetry is the independence of the initial conditions. But in the weak washout, such a process doesn't occur almost. So the initial asymmetries are not erased, so that it depends on the initial abundance of heavy neutrinos, or whether it is a Bully abundance or the initially the zeros number density. Quantitatively, we can solve the following Boltzmann equations for the B minus L symmetry. This is a washout term which gives the exponentially decreasing behaviors of the B minus loss matrix. The first one is correspond to the inverse decay, WIDs, and the second one is Lepton numbers by lighting scatterings with the unit of the one, and the third one is Lepton numbers by lighted by the number 2. This is the typical process channel, so via the scattering, the Lepton numbers here is of this curly L is 1, and here's L is 1, and alpha is -1, so the Lepton numbers are highlighted as the number of the 2. And such a gamma d is given by the such a thermal factors, and the y equilibrium is given by the equilibrium number density from the thermal statistics. So by solving the such a Boltzmann equations for the B minus asymmetry for the each parameters, k is smaller than the 1, this is correspond to the washout. As you can see in the here the jet, the variable m1 over the t, this is the when the decay start. But in the washout case, the k is smaller than the 1. This means that the coupling is small, and the decay occurs light. And the initial abundance here is number density of the n1's zeros in this case. This makes the abundance of the n1 cannot touch the equilibrium. So the happening between us n1s is in the other equilibrium in the older cosmic period. But for the strong washout case, k is larger than the 1. The decay occurs before the z equals to 1. And the initial B minus asymmetry is erases, and the final ones are independent to this initial condition. And the number density n1s can follow the equilibrium density because of the large interaction rate. Next, I will turn to the CP asymmetry epsilon. The epsilon is defined as the difference of the decay light. Here, this is the definitions. And the CP asymmetry epsilon becomes a non-zeros in the interference term between the 2e and the loop level term, and this gives the imaginary path of the equal matrix, which is related to the CP bar lighting phases. And if we calculate such interference term, the typical formula of the CP asymmetry epsilon is given by the following form. So in the denominators only the y squares, the equal matrix remains, and numerator there are the imaginary sort of the squares of the equal matrix terms remains, and from the loop term there is two terms that turns out. The first one is a vortex. For diagram, this is given by the such a form, and the sharp energy loop such a form, where the n is the solid lines correspond to the having neutrinos around the Lepton double for the fermion, and the dashed lines correspond to the Higgs double for its color field. In the hierarchical regime, when one having neutrinos flavors is extremely smaller than the other one, then this parameter x, the light year between the different generations of heavy matter neutrinos, becomes larger than the 1. And in this case, the vortex and the sharp energy terms are reduced into such a form, and the CP asymmetry epsilon becomes such a formulation. But in the degenerate regime, when the different generation of heavy neutrino has the similar mass, then the epsilon of the sharp energy loop diagram gives such a form. This can be obtained by the optical theorem because a different generation of heavy neutrinos are mixed via the loop diagram, and by the optical theorem we can obtain the propagators, and this gives such a denominator form. And when the different generation of heavy neutrinos satisfy the resonant condition, then this epsilon can be enhanced, which is called the resonant leptogenesis. And to explain the observed baryon symmetry of the universe to minus 11, this is polar practice. This is efficient factor. So the epsilon shift 10 to the minus 8. For the unbelievers, once a single heavy neutrinos and considering the single active neutrinos and the strong washout K is decay parameters, capital K is larger than the 1. And in this case, epsilon has the order of 10 to the minus 8, and to explain the inner baryon symmetry of the universe, the heavy neutrino mass should be larger than 10 to the 9 ZB, which is called the David's Ibarra bound. If we consider the flavor effect of the active neutrinos, this bound can be smaller as 10 to the 8 GB. And also in the resonant leptogenesis, this bound can be relaxed as heavy neutrino mass to the 1 TB or even more below. And such a 1 TB scale of the heavy neutrino is quite testable in the collider test serial experiment for the caesarium. But unlike the such heavy neutrino mass, the CP piles cannot be determined by the leptogenesis because this does not require the specific values of the CP phases. So now I'll turn to the flavor effect. Because Euclid interactions that get into the equilibriums in the different states of the cosmic history, so the B minor symmetry for the reposing in the each flavors separated for each cosmic time. So the Euclid interactions given by such a form, where H is Euclid coupling for each flavors, electron, mu, and tau, and this gammas can be obtained by the dimensional analysis. For the high temperatures regime, temperatures rather than 10 to the 12 ZB, the total lepton symmetry is evolves as a single value. But in the intermediate regime, temperatures below the 10 to the 12 ZB, the tau Euclid interactions are in equilibrium because the Euclid coupling for the tau leptons is larger than the other leptons. So the B minor symmetry deposing in the tau and the other ones is behaves to the separate value. And when the temperature is below than the 10 to the 9 ZB, the muon Euclid couplings is in equilibrium, so we should track all the symmetry for each flavor. And accordingly, the CP symmetry we choose the sums over each flavor, and for the Boltzmann equations, the B minor symmetry is deposing to the other each flavor. So if we considering such a flavor effects, we can relax the David-Ibarra bound because some asymmetry is still survives, some asymmetry is erased by the strong washout. So in such a flavor effect, the David-Ibarra bound can be relaxed to the 10 to the 8 GB that I mentioned. And in such a flavor leptogenesis, we should solve the density matrix equation DME because some Euclid interactions are in equilibrium, but the other ones are not. So these are partial interactions. So the leptons are neither coherent or the fully coherent. Some are in the one flavor, but some states is superpositions of the three flavors. So we should solve the density matrix formalism. In this case, the B minor symmetry has off-diagonal term. The off-diagonal terms correspond to the coherence between the different flavor, but the diagonal elements represent the flavors, the symmetry deposing in each one. So this is the density matrix equation, and here this is washout terms by the anticommutative between the washout terms and the B minor symmetry, and that the binary term is correspond to the coherent oscillations with the flavor superpositions. Aladdin, we mentioned the one-way to low-scale heavy neutrinos, leptogenesis, resonant ones with the nearly degenerate of the heavy neutrino for the degeneration. And the other possible one is ARS leptogenesis via the CP lighting oscillations of the stellar neutrino. And such a both resonant leptogenesis and the ARS leptogenesis are quite testable in the clad experiment with such a low-scale heavy neutrino. For such a GB or TB scale of the heavy neutrino capital arm, the Yukawa coupling is small accordingly by the Kasashibara parameter junction, so the interactions are also weak. And the stellar neutrinos that produces by the scattering and still this is out of equilibrium do not follow the equilibrium number density. And such interactions is the people, so the producer stellar neutrinos in the state of the current superposition of the each flavor. And when they propagate that they have the oscillation with the frequency of the frequency with the difference of the heavy neutrino. This is a similarism to the active neutrino oscillation. And because the mixing matrix between the active and the stellar ones contains the CP lighting phases from the Kasashibara parameter junction. So such a complex phases makes the different probabilities for the lepton and the anti-lepton and eventually generates the asymmetry. So we can solve the following equation for the number density considering the stellar neutrino oscillations with the CP lighting phase in here, so there are some additional thermal potential effects inserted in here. And to realize such ARS leptogenesis, the mass splitting between the each monomer neutrino mass should be the small enough to give the stellar neutrino oscillation. And there's the additional thing in the leptogenesis, like the spark theta process, which redistributed regenerated asymmetry and the thermal field theory corrections with thermal masses of the Higgs will have a neutrino and the anti-effect. Rather than focusing on the first one, we can consider the second generations. And the Higgs decay leptogenesis near the electroweak phase transitions approach, the Higgs can decay to the lepton and due to the thermal mass of the Higgs. And we can add the additional scalar which can assist the decay of the heavy neutrino. Also, we can insert the burst of the fusion transitions with the bubble dynamics and some gravitational wave signal is expected in such a scenario. So today we discussed the several factors of the leptogenesis. First one of strong and weak gases out, and the second one we talk about the CP asymmetry with the David Zivara bound, and this can be relaxed in the ARS and resonant leptogenesis with the low energy scale of the heavy neutrinos, and the playable effect also can have.